All right. Thank you, everybody, for being here. This is the final presentation for the Army Educational Outreach Program project done at College of Marin. We thank Terra High School, the Las Cumbres Observatory, AOP, and College of Marin for the opportunity given to us. And today we're going to have our students, our intern, Ramiro Velay. Ramiro, take it away.
Okay, thank you. Hello, my name is Ramiro Velay. I go to Terra High School and I'm going into 10th grade. And I did this work in the College of Marin, and today I'll be doing my presentation on the photometric cross calibration of astronomical transients. Okay. So what we're going to talk about today is telescopes and charged coupled devices, also known as CCDs, the electromagnetic spectrum, the Las Cumbres Observatory and the Gaia satellite, astronomical transients, the discovery of new transients, and my conclusions and future work. So telescopes. Telescopes are a type of instrument that are used to look at the sky and planets. Galileo was the first person to look at the night sky with a telescope, and he would take notes. Telescopes back then were called spyglasses, and they were mostly used for terrestrial purposes. The main types of telescopes today are refractors and reflectors, and astronomers today use big telescopes with mirrors instead of only lenses. Um, so so what you see right here in this diagram on the bottom left is it's like how the telescope works. So the light goes into the telescope and it goes into the eyepiece, into your eye, and then reflects back to let you see whatever you want, like the stars and stuff. And this right here is the Keck telescope, which is 10 meters wide. And these are a refractor and a reflector. CCDs. CCDs, which are also known as charged coupled devices, are a silicon-based multi-channel array detector of ultraviolet, visible, and near-infrared light. It is used similarly like the detectors in camcorders or digital cameras like in cell phones. In a CCD, photons of radiation that hit any part of the detector generate charged particles called electrons. So the way that the CCD works is the light goes through the lens and it goes into the CCD chip, then it goes into the computer, and then it lets you take like a photo in this case if you want to take a picture with a phone. And the brighter the object is, the more energy it gives. Uh, and more about CCD. So a CCD is a device that takes the light from stars and gives it brightness measurements so that then scientists can determine its magnitude, which is useful for determining how far away it is. So this right here is Gaia 19 BWS taken from the Las Cumbres Observatory, which was taken with a CCD. And so another diagram right here that shows how it works is the photons hit the sensor and then it turns those photons into electrons to make them take a picture. The electromagnetic spectrum. The electromagnetic spectrum is the range of all types of electromagnetic radiation. Uh, some types of electromagnetic radiation are visible light and microwave and radio waves, and others include microwaves, ultraviolet light, X-rays, and gamma rays. Electromagnetic radiation is expressed in terms of free energy, wavelength, or frequency. Frequency is measured in hertz, wavelength is measured in meters, and energy is measured in electron volts. Um, so this right here on this picture on the bottom is like Jupiter taken in different wavelengths. So the one on the middle is how we would normally see it, which is called with a visual lens, and this one on the left is taken with a microwave, and the one on the right is taken with an ultraviolet. eh, Yeah. And this graph up here shows like how the electromagnetic spectrum works. And so in the middle, you see like the light that you could see like the sun in a light bulb, but the one on the right is like X-rays and yeah, X-rays which you could see on which you can't see actually on the right, but you can feel them. And the one on the left is like cell phone towers and radio signals. Uh, yeah. Okay, and then more about the electromagnetic spectrum. When you look at the Andromeda galaxy through different wavelengths, it's like how you would normally see it through a telescope with the optical wavelength. But then when you see it through different wavelengths, it looks like completely different galaxies. So like for example, the optical right here is how you would normally look at it. But if you look at it through like a microwave, you can't really see like the other stars around it, just the galaxy. And same with like infrared and X-ray. Uh, the Las Cumbres Observatory. The Las Cumbres Observatory is a global telescope network of telescopes that are 1 to 3 meters in size. It was founded in 2005, and it is made to study astronomical transients. They are fully robotic, which allows them to make observations every night, and they are very efficient and productive. Gaia. The Gaia is a mission to make a 3D map of the Milky Way galaxy to let us know about the changes over the centuries. Gaia will provide measurements with the accuracy needed for a census of 1 billion stars. This amounts to 1% of the galactic stellar population, and its key sciences are photometry and radial velocity. Astronomical transients. Astronomical transients are events that happen in a short time and space. These events can also take up to weeks and even years. An example of an astronomical transient include an exploding star like a supernova and gamma ray bursts. So this right here is an example of a supernova, and this right here is a video of showing how it could look like. Okay. Oh, what? Okay. Uh, the magnitude system. The magnitude system is the scale that shows how bright a star appears. The brightest star would be in the first magnitude, and the faintest star that you could see with your own eyes would be in the sixth magnitude. Stars that have a 5 magnitude difference means that one is 100 times brighter than the other. For example, a -3 magnitude star is 100 times brighter than those that are +2 magnitude star. So like for example, right here you can see in the graph, but you can see in the graph like Venus and the sun, they are very bright, and like in +6, that it's the faintest star that you could see with your own eyes. And but you can see that like Venus and the sun is on the left, but you can still see them, but it's because they are very bright. Filters. Filters are devices that let you select only a piece of the optical electromagnetic spectrum. For example, you can choose to only see red light or to choose to only see blue light. The most common broadband filters that are used by astronomers are ultraviolet, blue, visual, red, and infrared. In many catalogs and databases, you see, for example, B-band and V-band magnitudes for stars. When astronomers measure the magnitude of a star through these filters, they often use the name of the filter to describe their measurement. For example, you can determine the temperature of the star comparing the R-band magnitude and the B-band magnitude. So like right here, you can see in the graph, so they, the, uh, so like right here, they produce more red light than the blue light, and this right here produces more blue light than the red light. Okay. And supernova. A supernova is the process of when a star explodes and it dies. It can sometimes even be brighter than some galaxies. Supernovae can radiate more energy than the sun can in its entire lifetime. They are some of the most powerful explosions that takes place in space. The oldest known supernova is the RCW 86, which some Chinese astronomers saw during AD 185. Quasars. Quasars are galaxies with a very massive black hole in their core. Even when very far away, the cores of the galaxies shine much brighter than stars. Quasars are one of the most energetic objects in the entire universe. Radio quasars represent about 10% of the known quasars, but we are still studying them in detail. Microquasars. Microquasars are the galactic binary systems that are made out of a star and a compact object like a black hole that eats up matter from its companion. It gave the rise to relativistic jets, which are beams of particles moving at the speed of light. The word microquasar was used for the very first time in 1992. The calibration procedure. So we observed 4 objects with LCO. These objects were identified by Gaia to be new transients, but their exact nature was unknown. So the way that we did this was we calculated the R magnitude of 10 stars in the LCO images. Then we used the Gaia archive to find the Gaia magnitude of the same stars. Then we calculated the offset between the LCO R band and the Gaia G band. Then we applied the offset to Gaia's source LCO mag. Then we put our data points in the graph to build a full light curve. Okay. And here are our results. And yeah. So what could they be? One of these could be a supernova type 2N, and the other could be a nova, like the SX Cygni right here on the bottom right. And because of this analogy, we think that the Gaia 19 BMU is a cataclysmic variable, like the one on the bottom. So what did we learn from this? So we want to study astronomical transients. So we took the data from LCO and we combined them with Gaia's. Then we found the brightness of the object and we built like the light curves for the 4 objects. And so now we think that one is a new supernova and the other one could be a cataclysmic variable, and more observations are planned for the other 2 sources. And yeah, that's it. Thank you.
Good job. All right, well done, well done. Okay, so anybody, now the floor is open. So if anybody has any question or curiosity about the project or any slides that you saw or anything, please, this is the time. Question from students also encouraged in case anybody has any questions on how we did this.
I was just going to ask, how much did you know about astronomy before you started this project, and how much do you feel like you know now?
Well, not really that much. Like I only knew about like the planets and stuff, like the stuff that they teach you in school. Like I didn't really know much about like supernovas. Like I knew about what they were, but not really that much. So yeah, I learned a lot during this.
Great.
Thanks, Eric.
I wanted to ask a question, I think, about the CCDs. I learned about that today. Did you get to handle any, or did you just kind of learn about them?
Yeah, I just like mostly learned about them. Yeah.
I think I showed one.
Yeah,
in
he
the lab,
he
right?
showed me one, I'm
Saw
pretty
one.
sure, but I never really like it was just for like one day, I'm pretty sure.
Yeah.
Like I mostly just studied about them, but they were still pretty cool to learn.
Awesome, thanks.
Anybody has any other question? Juan, Brandon, Amadiel, Curtis, any question or curiosity from your end?
Oh yeah, I guess one thing. I was wondering, where do you get the data that you use for all of your studies?
But like my data, right?
Yeah, like the ones you like made the graphs out of. Yeah, like where do you?
Yeah,
get
like the
data from?
graphs. Okay.
Mhm.
I got them off of the Gaia archives. So yeah.
Oh, okay.
So images from LCO come from our own telescope. So we observe with LCO, so the data are ours. The Gaia data instead come from the archive. So this object, these images have been already processed by the NASA Gaia archive, and so you can essentially either download the images or look at specific objects. So for the graph, Ramiro, can you show again your PowerPoint where you have the results page? So the LCO data that we collected were analyzed by another students this spring, Liane Barreiro, a College of Marine student. And all these points that you saw, all these blue points are Gaia data. So they come from the archive, except the one that are marked with the arrow. Those are our own data. And Liane did the preliminary analysis on those images. Those images look like the slide before. Can you go the slide before, Ramiro? Yeah, that's those are real images that we took from LCO, and so we analyzed the images ourselves.
Out of curiosity, you mentioned one of those you think is a supernova. Which one is the supernova?
It's go to the next slide, number 18. Oh, you have there. Yeah, no, that's correct. 19 is fine too. Yeah. So BWO is a possible supernova 2N because it had this very long tail. And the one on the top, the one that's marked in red, the top left, it's a different supernova 2N observed by a different telescope. And you can see the similarities. There's a decay at the beginning, and then you have some bumps, but you do see this very slow decay process. Like it's going
like a long, slow decay process.
That's right.
That's how you know.
That's right. Mm-hmm. Yeah.
Okay.
Yeah. Different type of supernova has sort of a different type of decaying. So looking at the timeline and the type of decrease in brightness, it looks like that.
Cool.
Okay, Diane, have you learned anything about that now that you saw the presentation?
Let's just say I'm impressed and leave it at that.
Great. Mission accomplished. All right. So if there are no further questions, let's thank Ramiro again. Thank you so much, Ramiro, for being with us this summer. Great presentation.
Thank you.
Thanks a lot.
Thank
Great
you.
work.